Welcome, everyone. My name is Brittany Todd, and I'm a member of the Fabric Leadership Team. Thank you all for joining us today for the 8th installment in our Stitching Together Innovation with Fabric users led by Cody Bumgardner, Vaiden Logan, and Mitchell Klusty. Next slide, please. Before we begin, I would like to share a few housekeeping items. This webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled. If at any point you have a question, please type it into the Q&A box at the bottom of your screen, and we'll answer it during the Q&A session. Last, this webinar is being recorded and will be shared with all registrants. Next slide, please. We are joined today by our presenters, Cody Bumgardner, Vaiden Logan, and Mitchell Klusty. Cody Bumgardner is a computer scientist in medicine. Cody's primary interest is in the advancement of distributed systems, high-performance computing, and artificial intelligence in healthcare. Prior to his current appointment, he has held several technology leadership positions, including Director of Enterprise Systems and Development, Chief Technology Architect, and Director of Research Computing. In addition to a 20-year career in technology architecture and operations, he has led numerous research efforts, including international research federations and privacy-preserving data collection, contract support of national research infrastructure, and the development of clinical and research data management systems across laboratory, imaging, and genomic domains. He enjoys working on innovative projects at the intersection of AI, medicine, and distributed computing. Additionally, we are joined by Vaiden Logan. Vaiden is a computer engineering graduate from the University of Kentucky, currently pursuing a Master of Science in Computer Science. He focuses on large language models, LLMs, the DGX computing cluster, Cat Talk, and LLM Factory. Vaiden's expertise lies in computer networking, and he has experience collaborating with computer scientists and data scientists. He is currently focused on leveraging LLMs for summarization tasks and designing systems that integrate AI for a variety of applications. And last, we are also joined by Mitchell Klusty. Mitchell is currently pursuing a Master of Science in Computer Science. While completing his Bachelor of Science, Mitchell earned a cybersecurity certificate from UK, thus gaining a strong foundation in secure systems designs and analysis. As a software developer at CAAI, Mitchell's knowledge of security is imperative to the operations of the department. In addition to cybersecurity, he continues to specialize in the development and application of LLMs. He is the designer and lead developer of LLM Factory, CAAI's innovative self-service LLM tool that empowers researchers and university members to leverage AI solutions efficiently. Mitchell's passion for LLMs and his expertise in cybersecurity add value to CAAI. I will now pass to Cody to start the presentation.
Everybody. So what we'll talk about today is some work that we developed along with this grant that we received. I think we're about a year into it. And the problem we were trying to address was that with medical imaging, sometimes there's not an availability of imaging and it's large. And unlike cancer, these Alzheimer's disease and images of the brain, you can't acquire them until, at least for the pathology images, until the person's deceased. So the image and data sets are relatively large, but they're also spread out across different groups. So we received this grant with our collaborators at a number of institutions to try and be able to do analysis and treat a bunch of images that are distributed around the world as if they were at a single location. So the first aim is to develop that platform that will run, could be cloud resources, could be local resources, but essentially computation in place for being able to share and analyze the data. Once that platform is built, demonstrating federated machine learning across those locations. In some cases, we need to pull down – all of the images. In other cases, we just do part. Next slide. So what we'll talk about today is some work that we developed along with this grant that we received. I think we're about a year into it. And the problem we were trying to address was that with medical imaging, sometimes there's not an availability of imaging and it's large. And unlike cancer, these Alzheimer's disease and images of the brain, you can't acquire them until, at least for the pathology images, until the person's deceased. So the problem we were trying to address was that with medical imaging, sometimes there's not an availability of imaging and it's large. And unlike cancer, these The thing we usually get, the question we usually get, and we don't get this as much anymore, certainly as some cuts have occurred, would be why don't you just put this all into some cloud resource? And in most cases, it's because of the cost itself. I mean, just to store, if you look and see how we have to keep these slides actively in file-based or block-based storage to where they can be utilized, the costs get exorbitant very quickly. And then even if we process them locally, the cost could be $25,000 to $35,000 to pull down a large data set to process it alone. So what we then said, well, now why don't we just leverage existing investments? That's a little easier said than done in hospitals. It's very difficult, and a lot of times the people that have the image sets, the researchers, maybe don't even control the infrastructures that they have. It's increasingly hard to operate inside of hospital networks with zero trust and other restrictions that you can't even communicate out without knowing exactly the application that you need to talk to. And in general, in these secure environments, the storage systems and the image management systems are considered internal services, usually attached to EMRs or other really secure networks, and not part of the DMZs. And there really isn't a good way to bridge those gaps, at least not from the healthcare IT perspective. And different participants have different resources and the ability to control that. So, for instance, at UK and at Emory and other places, we have people that technically have resources that would allow us to host a public repository where someplace else, maybe they actually have the storages and have the images, but they can't actually host it, and it would be really difficult to make that happen. Next slide. Yeah, so why do we use Fabric? Now, we could have, like I said before, we could have just created a bunch of resources across the country and public cloud, and could have done that, still do that. But we knew Fabric from the standpoint of being able to programmatically configure the network topology and other resources, because we have to be able to when we're building this big federated system, there's different configurations, there's international configurations, even within our hospital, that there's layers and layers of network infrastructure and middle boxes and firewalls. And we need to be able to show to the NIH that we can actually deploy and develop these things and deploy them at scale. So the ability to do that was very important. Need to be able to simulate and not just simulate, but actually see what the impacts of real world latency are. We might be able to pull a single patch of an image, but then when we have to pull a full image, or a data set is dependent on something in South America and another is dependent on something in Atlanta or Kentucky, what does that actually look like in a real world area? So we're using Fabric to deploy this infrastructure and then layer on top of that our own abstraction of infrastructure to be able to solve a lot of these problems where we don't have direct access to the resources, and maybe a machine at UK can't, University of Kentucky can't actually talk to a machine in Emory, but they can both talk to some middle box that we can bridge that connection through. Next slide. And this is what it looks like on a high level perspective, and that the central data trust isn't actually central, it's federated, but what we're trying to do is to treat it like it's the same way. So we have image generation in some areas, we have high performance computing in other areas, but a lot of the effort is to take curate data sets and then make them available in a way, regardless of where they're stored, that they can be used any place that they need to be used. So that's part of AIM-1. AIM-2 involves data set annotation, which means that you need to be able to interactively view the data. So it isn't just a content distribution network. We have applications that we have to be able to in a particular data set, maybe one image is in one location, another image is in another, and it needs to be the same experience. Data set generation, which can be a offline operation, would pull from multiple sites, and then the same thing with review and any of the automated machine learning. In many cases, a expert pathologist will have annotated a certain section of the image or brain, and then that's used to pull the fairly small patches from, instead of just moving the entire image itself. So this all has to happen in a way that, as far as the pathologist and other folks that are working in that domain, that they don't know that one machine is in one place and one image is in another. Next slide. And the way we do this and on top of Fabric is, like I said, the goal is to have these islands of network resources connected. And from the user perspective, they look the same. The way that we do this is we use multi-protocol agents. So in this case, agents, a bit of code that runs along adjacent to the resources. And what that does is let it basically serve as it makes connection to a message broker. So any agent, if we can get one agent connected to any other agent in the world or chain them through those agents, we have a computational network that we can bridge across, essentially the globe. And the image below there, you can see what that looks like. If you were to look at the S3 compatible namespace, which we have a custom developed S3 server, the S3 buckets on the left, even if whether they're actually stored on the right or if they're stored on the left, meaning at different institutions, it looks like one big global namespace. The other thing that we can do is to forward tunnels, which is what we'll demonstrate today. So even though we're on a IPv6 network from Fabric standpoint, and we have different firewalls and blocks in between them, we were showing where we'll have multiple hops to go through that. But since one agent can connect to another agent that connect to another agent, we can actually do an IPv4 tunnel or 6 between those locations. So you may think, well, it sounds like you're circumventing a lot of security practices, and we are, but the way that we're doing it, we find it to be even more secure than if we were just opening things up to the world, because what you're doing is, even though we're tunneling data from point A to point B, it's not exposing point A and point B to the rest of the world, meaning that as you can see in that image, the local storage and local resources look like they're local to that particular environment. So really all we're doing is hopping through these different agents. Next space, or next slide. Yeah, go ahead, Mitchell.
Yeah, so like Dr. Bumgardner introduced, one of the projects that we're working on with this infrastructure is the Digital Slide Archive, Brain Digital Slide Archive project, which is an NIH-funded project that is intended to kind of be a collaboration of different institutions. And one tool that we use in this project is called Digital Slide Archive, or DSA. And this is a pretty well-established tool. It is used for creating or storing and viewing large slide images and creating annotations for those images. This was developed under another NIH grant several years ago, and it's pretty widely used. So, onto our project, Brain Digital Slide Archive. What that is a federation of different institutions around the world to be able to kind of combine neuropathology slide images together and the annotations for those to be able to train better models by sharing data. So, one of the problems that neuropathology has is that there's a lack of slide images that have good annotations that can be used for ML data because, like Dr. Bumgardner mentioned earlier, the images are just kind of hard to come by because the patient has to be dead for you to get the images from them. So, the goal of this project is to kind of take everyone's projects from around the world and different institutions that are members of this project and combine them into one repository that we're able to pull from and be able to create models from that larger data set. A problem that we run into with setting this up, though, is that when we have distributed DSA instances around the world, it becomes really hard to manage the metadata across all of those different nodes for both case and slide level, and for managing the access control to those images and making sure that the only people that are able to see those images are the ones that should be able to based on the data agreements that we've created. We also run into firewall restrictions that prevent proper access to the slide images. So if one person in at Emory has slide images that they want to share with us, but their DSA instance is behind the firewall that doesn't allow them to access that, that causes an issue for us being able to make that image available to the other member institutions. So our solution to that is what we're calling BDSA Hub. This is a site that does centralized coordination of metadata and the access control for all of the images. It manages both of those things. So if we look at the image on the left, that shows the metadata hierarchy for how the BDSA hub manages everything. So we store it in a hierarchy of collection, case, and then slide. The case metadata is things like your demographic data about each individual patient that a set of slides makes up, and the slide metadata is the things that go into the image, such as the brain portion, whether it's the right or left side of the brain, and the stain format uh, of the image. And then we also manage access control. So we have a strict policy based on data use agreements that are developed through the project to ensure that the only people that are able to be granted access to a specific image are the people that are either members of the institution that own the collection with that image in it, or if that collection has been shared to that to an institution that that person is a member of based on a DUA. So I will now showcase DSA Hub. So here's kind of the hierarchy that we talked about, just an example slide. This is a set of cases in a collection, and then we can see the collection and the case metadata here for each one of those. And then these are links to each of the DSA collections that store those images. And then we can go into the slide level. We can view the slide level metadata, and then we can also be linked to the slide in the DSA instance. We also have a setup with BDSA called projects. So what this allows us to do is we can collect sets of slides based on our DUA principles by only allowing people that are on specific projects to be able to access these cohort of slides that we're going to be put together. But I'm able to specify a specific collection that we want to use on collecting these slides into a cohort for this project, and then add metadata filters. So in this case, let's say, for example, that I want to set where npsex equals 2, then I can submit those filters, and it will add all of these slides into this collection that is a cohort of slides that we can use to train a ML model on specific images where the metadata filter uh, has been achieved by all of those slides. And then we manage the access to who is allowed to see these slides based on those DUA principles that I talked about. So yeah, so once we use the project and we're able to collect all the slides that have the specific metadata that we want for a given model, we're able to extract tiles from the image using the DSA API. So this allows us to take an image like this, and once annotations have been performed by, usually these are done by hand, uh, the image can then be segmented into something like on the right, where it's divided into several chunks, and then those chunks are then used to train models based on their labels, and uh, they're essentially like each one of those chunks is given to the model with the label, and then a huge data set of that will be passed in through training, standard machine learning model training, and it'll produce a segmentation model. And then we're able to take a new image that the model hasn't seen before and pass it to the model and receive as a response the segmented image of that model, or of that image rather. So what we want to use Fabric for is we wanted to address the remaining problem of securely connecting the DSA nodes with the network restrictions in place based on institution firewalls. We wanted to be able to create a unified network of DSAs across essentially the entire world, and be able to add institutions wherever we want and pop up nodes and be able to hook them into our system and create secure tunnels to transfer data securely and allow those tiles to be transferred from one DSA into another, uh, like anywhere that you would want to be able to call that from, and allow you to train those models from there. We did this by setting up 4 different nodes on the Fabric network, one in New York City, one in Salt Lake City, one in Los Angeles, and one in Atlanta. And we tested our ability to use the CRISO framework to set up agents and global controllers and be able to uh, develop those tunnels up so that we can transfer data between the entire system. Under the hood, what does this look like? So we have one globe controller running on a public UK server, and then we have several different agents running on the Fabric nodes. We make a call to set up the tunnels on each of those systems, and uh, the S-tunnel plugin will be deployed on the global controller, which will then forward this ports from the global controller to each of those agent nodes on the Fabric network. And then we're able to connect into each of the Fabric nodes directly through the global controller and make any requests through the accessible global controller onto the inaccessible Fabric nodes that are behind the Fabric firewall that we've developed. We also created a dashboard to be able to look at this network, so you can see that on the top right there. Essentially, that will show the developed nodes that have been added to the infrastructure, and then what the data transfer speeds are at any given time. I'll now hand over to Vaiden, and he will continue.
Yes, thank you. Let me share my screen. Okay, Mitchell and Cody talked about BDSA and CRISO and thank you. And kind of the overview of this experiment. I'm going to talk about the specifics of how we used Fabric to do this. So the first thing to do was actually create our Fabric slice, which of course you do by calling the Fablib API and just creating a new slice. I then added 4 nodes to that slice. In the diagram on the last slide, you can see that these are the 4 nodes that are behind firewalls, in this case, the Fabric firewall. For the parameters of this, I just used very small nodes, so we only have 4 cores, 8 gigs of RAM, 50 gigabytes on the disk, and then we used Ubuntu 22. After creating all of those nodes, you call slice.submit, and that actually spins up your slice with those nodes. You may notice that I did not add any networks to this, and this is because these nodes are behind separate firewalls, and so they wouldn't really be able to communicate in the real world. In our experiment, these will only be able to talk to the CRISO global controller so that the tunnels can be created, which I will talk about a little bit later. But first, I'm going to talk about the sites that we chose. So for our nodes behind Fabric, we chose Los Angeles, Salt Lake City, New York, and Atlanta to host these DSA instances. We just chose these because they're all on the 100 gig loop that Fabric has, and they're also spread out across the country. So after the slice was set up and all the nodes were up, what did we do to actually put the software onto the nodes? The first thing was to download the CRISO agent onto the nodes. You can see in the third line of the command, we just do a curl from the releases on GitHub to do that. Next, we install Java, which is how you run the CRISO agents. Then we install Docker, because that's what runs the DSA instances that we spin up on each node. And then there's some extra configuration to make sure that the Ubuntu user, that's the default on each Fabric node, can actually run Docker with the correct permissions. Then you see that I iterate through all of the nodes in the slice, and I execute this command as a thread, which allows this to run in parallel, or all these commands to run in parallel across the nodes so that things get spun up a little bit faster. Then I wait for the results, and when these are all installed, those results are printed for convenience. So after everything is installed, we can actually turn on these CRUSO agents so that they connect to the global controller and so that these connections can be tunneled. So this is pretty simple. It is a Java command where you just pass in a few of these parameters. You specify that this CRUSO agent is actually an agent, and then you specify the IP address of the global controller that we're connecting to, as seen in this D regional controller host line. And then this command is run on each of the nodes. Again, I use this execute thread command. It also has this output file parameter where you can pass in a file where the CRISO logs will go. And that's for the convenience of the user so that they can see what's actually happening with the agent without getting into the node. They can just see it from their Jupyter hub. So why did we use Fabric for this? First of all, Fabric just enables experimentation in distributed computing, which matches the nature of our experiment. We need to be able to spring up these DSA instances at various locations, because that's how it works in the real world. We have DSA instances at all these different institutions. Fabric allows this to happen very conveniently. You can create a slice with any set of nodes and any networking between them. And then after you have that, you can install whatever software you need very easily using their API, as I showed earlier. The Fabric firewall also matches some of the real world restrictions that we'd be dealing with. Since these DSA instances are behind institutional firewalls, you can't just go and get the data. You need some sort of tunneled connection. And since Fabric has this firewall that prohibits a user from just dialing into a node, it matches that restriction very well. The last thing I have on here is the Fabric knowledge base. I have found this to be super useful. The guides have instructions for creating slices and nodes and the networking, and then various other guides that can be useful. And they also have forums for getting help. I have asked so many questions on there, and I've always gotten a fantastic answer that has solved my problem. So I'm very grateful to the people involved on Fabric for that. And then next, I have a demo I'm going to do. So here's my Jupyter Hub. So the first thing, or this demo is just going to go through running these DSA instances, connecting the Criso agents to the global controller, and then creating these tunnels. And then after these tunnels are created, I will download tiles by connecting to our global controller, which is also our public server, and downloading the slides. So none of these slides are actually hosted on this public machine, but they will pull from the Fabric nodes through those tunnels. So to get us started, I am going to start up the DSA containers. This happens very quickly. It's done in parallel across all the nodes, and then we get all the results. So it looks like all of the DSA instances were put up properly. Next, I'm going to run the Criso agents, and I'm going to open this dashboard so that we can see the connections being made. You will notice right now that there is no infrastructure connection, but there will be soon, and these logs should start appearing. I'm going to open one up real fast, and you can see that the controller complete up has started, and that the tunnels have been created. And in this dashboard, now you can see that these infrastructure connections are in place between the global controller and all the nodes in Fabric. So now that this tunnel has been created, we can download tiles. So this is just a function to download those tiles. And let me go through some of these parameters. We have a base URL. This URL is the URL of the public server that we connect to get the tiles. We have an API token and an item ID. The item ID is just the ID of the image that we're getting. And then we create this downloader where we pass in all those parameters, and then we download the region into this output directory, which I will go into. As I start this up, you should be able to see one of these links activate to show that data is being forwarded through one of these tunnels. So let's do this, and I will update this. Yeah, and you can see that this link has been activated because there's data flowing through. And then all of these tile images have appeared in this directory. We can access each one. So let me see what slides I have left. Lastly, just want to acknowledge the research reported in this presentation was supported by the National Institute of Neurological Disorders and Stroke and the National Institute of Health under this award number. But that's the end of my demo, and I'm going to pass it back to Brittany.
Thank you so much. I'm having video issues here, apologies. Thank you so much for that presentation. And now we will move to our question and answer session. So we'll begin with the first question, which is, how do you account for consensus agreement amongst pathologists before model training? For instance, 2 or more pathologists who look at the same image may not agree on the interpretation and possibly annotate different regions of the image. Is this an instance of quantity over quality?
I don't think this particular system is intended to solve that at its core, but what we do is allow for one of the first applications that was developed was actually by a pathologist. So even though we're providing a hub, quote, framework, they are developing a tool for different types of segmentation, so they can deal with that however they want. But I can tell you, as far as that question goes in the past, there's a number of ways to do this, and typically it's pathologist driven how they want to do it, whether it would be the outside borders or the inside borders or some consistency between those. In most cases, it's not like you have 100 people annotating a slide. You would know the rank of the pathologist, and when we're taking and doing the annotations, instead of it just being one annotation, you would know who did it, and then you would know whether that was a high school student, or somebody that's been doing it for 20 some years. The way that in what Mitchell talked about from the hierarchy of when you go into the hub site, you go into a project first. So it's not like you go and start clicking around looking at images. So there'll be a protocol for how things are annotated and what tools to use and that sort of thing as you go through the hub site. So any annotations that were done, say, for gray and white segmentation for project A won't necessarily show up on project B. So if there was a different protocol, they can be dealt with it hierarchically while still using the same data. So I guess the shorter answer is, however the project leads want to deal with consensus, we just provide a method that they can do that on a project per project basis while using the same underlying data and system.
Great, thank you so much. The next question is, why use Fabric instead of putting it in a cloud provider, which has been common in the past?
I don't know if one of the other ones wants to comment on that, but a lot of it was we had familiarity with Fabric and knew what it could do, even going back to the Genie days before Fabric. And a lot of this is bringing things up and down and moving lots of data around, which we know that can be very costly in public clouds. So technically, we could have done it public clouds. Even with local OpenStack deployments, we could have done similar things. But you don't actually, when we go to the NIH and say, we have this really great thing working, we've simulated it, and it's all great. That doesn't have the same impact as saying, all right, we've physically deployed things across the country or across the world. So you either pay for doing it in the public cloud, which could be very costly if we're moving around petabytes of images, or do it in Fabric, which I think Fabric has been really good for us for that credibility.
Great, thank you so much. The next question is, isn't the process circumventing security controls that hospitals have put in place?
100%. No, there's the things that are put in place. So we have our own facilities. Some of our HIPAA is here, and then NIST, and then you have high trust above that. So there are ways that you can get around doing this. But what we're talking about was that in many cases, if we're, say, in a hospital and we're pushing data out, and I work in the laboratory, we've had a bunch of laboratory systems up. Every lab machine phones home. All the genomic sequencers, all the automated test lines, all those things are already phoning home. So we're not doing anything that every company in the world isn't already doing. What we're doing differently, though, is that we're basically taking remote endpoints and then giving them a presence locally. So as far as our compliance people are concerned, we're exposing things to ends where we already have agreements, and potentially BAAs. If not BAAs, we have at least data use agreements. So in many ways, the compliance people prefer this approach to, say, opening up a firewall between two locations or establishing a VPN. So I think it's a better way.
Excellent, thank you. The next question is, can I use this? Is it available?
Depending on the pieces, yeah, most of it's in the public domain. So for instance, the DSA servers in the public domain, Creso is public. I don't think Mitchell, I don't know, have we pushed any of the hub code out? I don't think we have.
We have not yet.
Yeah, but there's pieces of it you can use it. Yeah, just contact us and we can tell you where to go.
Excellent, thank you. Next question, what do you hope to accomplish with this?
Doing all the talking.
I think kind of what we explained in the presentation, we just want to be able to connect different DSA instances across the world and be able to integrate them into our system to where one DSA could just be spawned up anywhere and connected into our system so that we can automatically just pull down slide images from it as soon as the annotations are done and the data use agreements are put into place.
Yeah, and part of it's that just making the data available too. If we were doing this for cancer, then a big cancer place may scan 1,000 slides a day, whereas, like I said, the person has to be deceased for to get these brain images because you have to dissect the brain and make slides with it, where they can take out biopsies in certain organs and do that while somebody's still alive. So you're talking about orders of magnitude less availability for the underlying data, which actually does degrade over time. So the part of it's a digitization of things that already exist, but then making that available for people to do certain things. And these groups have not historically been really tech savvy. So they're shipping drives if they're doing anything. So a lot of its first principle would be just making the data available, and the second would be doing things that we couldn't otherwise do. So for instance, one of our first major efforts, we're doing segmentation, but the first major thing we want to do is to take the data at these different locations and train the first neuropathology foundational model, which there's all kinds in cancer, but there's none in neuropath because there's just not enough data to do it.
Excellent, thank you. Last question, can AI be used in this process for automation?
I think so. I think that especially the pieces of connecting the instances through the Creso network would be, you could have an AI that is able to set up those instances, but it really depends on how you'd want to use that and how much you'd want to let AI run with that.
I think we've shown that in a precursor to this, we had a nice system that you could basically do your cohort discovery, and that would be label 0 is this type of patient, label 1 is this, label 2 is this. And that was we pulled the data together, and that was a manual process. And the automation there was to say, this is my cohort, and then I start adding data to the system, which has metadata related to classes. And then we'd say, well, if it gets above X number of new cases or 20% of the data set, regenerate a new canonical data set for this particular thing that we can then use for validation going through. So the couple ways where AI can be used is that we have the underpinnings for automation in terms of being able to describe what we want and how we want it. It would be using either text or verbal commands to say, this is the kind of patient that I want, and then figuring out what that configuration would be. And we've demonstrated that in other areas as well. So I think that would certainly be letting the AI or a model between tool calling and other functions describing what you want, having it build the cohorts, and then letting our existing automated training systems essentially do the rest.
Thank you very much. And as this was our last question, I do want to give another thank you to our presenters, Cody Bumgardner, Vaiden Logan, and Mitchell Klusty. And in addition to our presenter, we would like to acknowledge the behind the scenes team listed here who worked diligently to bring the webinar to production. So thank you very, very much to these people. Next slide, please. And also thank you to the audience for your participation in today's webinar. In addition to a recording of this webinar, we will also email everyone who has registered a list of resources. This slide deck will be shared along with our Connect With Us form, and we hope that you will reach out to the Fabric team for questions or support. Our webinar next month is Mastering Fabric Tips and Tricks webinar on April 15th at 3 p.m. Eastern. This webinar will be focused towards existing users and will focus on the topic of routed networks with performance enhancements via hardware offload. We would appreciate it if you could forward this information to any relevant users in your communities that you think may enjoy this. And as a final reminder, please submit your Fabric matrix and make sure your project descriptions in the portal is up to date, as we will use that information for outreach, including our website. Thank you again, and have a wonderful day, everyone.